Yeah, ladies and gentlemen, mesdames et messieurs, senores y senoritas, meine Damen, meine Herren, it's a great pleasure for me to welcome you on our tonight's webinar on the dawn of the hydrogen economy, recent developments and activities. It's a great pleasure for me again to welcome you on this Wednesday afternoon or Wednesday night at 7 o'clock in the evening about our lecture series about, let's say, green hydrogen. After we have learned last week a little bit about the activities of hydrogen in Tunisia and the ongoing activities and the, let's say, ambitious plans, what is going on there, we will tackle this week the question of hydrogen storage, and here in particular, hydrogen underground storage. And on this background, it's my great pleasure to introduce first two very competent presenters. On one hand side, we will have a presentation about hydrogen and Sol, the dream team for hydrogen storage. On one hand side, below ground, what is in the underground, what is the possibilities, the constraints, and the given options to store hydrogen below ground. And then we will have a presentation about the hydrogen storage in salt caverns, about the aspects which is above ground. So first, Hagen Bültemeyer from DBI in Freiberg and Leipzig here in Germany will give us a presentation about that. And then Lorenzi Laporta from ELF in Munich will address the, let's say, above ground aspects of these important hydrogen storage options. And then the second part of our tonight's webinar, Julian Jepsen from Herion and from the Helmut Schmidt University here in Hamburg in Germany will give us an update about hydrogen storage in metal hydrates. So from that point of view, ladies and gentlemen, you can expect an extremely interesting program tonight, and most likely also a lot of new insights and new developments in this area of hydrogen storage. So with this, I would like to conclude my introductory presentation, and it's my great pleasure now to introduce Hagen Bültemeyer from DBI. So please go ahead and give us your presentation about hydrogen and Sol, the dream team for hydrogen storage aspects of the below ground. So the floor is yours, and we are listening to your explanations.
Martin, thank you very much for this very kind introduction, and just give me one more second to share my screen, and this should be done by now. Thanks for the thumbs up, and very warm welcome to you, the audience, to this presentation here. It was announced we are now looking into the underground part, the subsurface, geological structures, and with a particular focus on salt caverns. My name is Hagen Bültemeyer. I'm the head of Department Gas Production, Gas Storage here in the DBI group. And let's get started. The presentation is split into two parts. Very brief part, short overview of our company and recent activities. And then the big one, hydrogen underground storage. With two distinct focuses, hydrogen storage capacities, and how does this impact our wellbore completion and the caverns itself, with then in the end a link to the surface facilities where Lorenzo is going to take over. Okay, just a few words about our company. We are a small and medium-sized enterprise located in Leipzig. We are a research and development entity, and we also do fundamental research. The latter one under our subsidiary, the Gas Technological Institution, which is located in Freiberg, where also I myself are located. Okay, we as a company always aim to cover the entire value chain of gaseous energy supply. And here on this screen on the left-hand side, you see a bit of our topics that we work on, but it's just an excerpt, not limited to that one, but where we dominantly is here put the hydrogen, and the weight, the balance shifted more and more to the renewable energies. That's just what the market, so to say, demanded. And of course, with our research activities, we always want to stay on the forefront of the developments. On the right-hand side, I showed a brief chart on hydrogen or general gaseous energy supply from production to distribution to storage to utilization. And very dominantly, I put the underground storage facilities in the middle of it because we consider them as a vital backbone in also the current energy system, but also in future energy system with renewable hydrogen. Okay. And one very recent example of that in practical real world is the REAL. In Germany, we call it Reallabore. You might have heard this term, real labs, loosely translated in English, large research project, but in an actual cavern on hydrogen underground storage as a backbone for regional energy supply for various customers, the first one of this kind. Currently, the works are ongoing in the surface facilities, but then in 2025, we will start with the below ground works and to have the cavern ready by 2026. Okay. Yeah. This picture was just, this photo shoot was just when the project officially started. Very nice event. Okay, then let's get started into the main part. This slide, you might pause by yourself when reviewing the stream afterwards. Just some, let's say, political figures, why hydrogen, why it's important. For this presentation, I will just go over it. But why do we talk about, in particular, about underground storage? What I put here in this chart from the, I borrowed it from the colleagues around Mr. Sterner, are different storage possibilities. And what is plotted here on the y-axis are the achievable withdrawal durations versus on the x-axis, the overall storage capacities. There are different options, heat storage, condensers, pump storages, and in those red bubbles here, the underground gas storage facilities. And all of those bubbles look more or less of equal size. However, please consider that the scales X and Y are both logarithmic. If you would linearize this one, it would be just one large red bubble, so to say. And this really brings us to the answer of the question, why? It is simply like this, that for regional and long-term energy supply and as a backbone for industries, entire regions, we really need large capacities in the terawatts range. And when we're talking about those things, we are almost exclusively ending up with the geological storages. Also, when we look at the withdrawal capacity durations, we at least want to achieve something in the range of several weeks to months. Just consider winter periods, 3 months, and for such a period of time, you need to have withdrawal capacities at hand. Okay. Don't want to downplay the other possibilities, but they also have their place in the energy system. But I think the necessity for this geological storage options is definitely there, and it is quite obvious. When we talk about geological storage facilities, we distinguish mainly between two different types: caverns, here plotted as a model on the left-hand side, and depleted fields, porous, depleted oil and gas fields, porous UGS facilities, plotted in a model on the right-hand side. There are some other geological types as well, but those two are the very dominant ones. And yeah, the focus of the next slides is on the caverns, and I will also give you a reasoning why. Okay, this slide here, for the course of this presentation, I also go over very briefly. You might pause the stream if you like, or during upcoming review. Some characteristics, or the main characteristics of the two different types, porous UGS and cavern UGS. And I highlighted it in the cavern UGS, those features that make them particularly interesting for hydrogen storage. Easy adjustable withdrawal and injection rates, by means of tubing diameters or simply number of caverns. Lower effort for gas treatment and very flexible in terms of operations. They can easily switch from injection to withdrawal and vice versa in very short term. And the porous UGS facilities, they are more on the baseload application side, and it's also very necessary that we consider them in our investigations and considerations as well, because some countries simply don't have salt caverns. But yeah, salt caverns are of particular interest. Okay, why this focus? I partly answered it already in the next slide. This question, why is salt and hydrogen maybe the dream team for storage, is a question raised from a mostly German perspective. And Germany in the European Union has the largest natural gas storage capacities, and most dominantly, the largest share of it is in salt cavern UGS facilities. That's a rather unique case compared to Europe or worldwide as a whole. There, the split is just the other way around. Porous UGS facilities are most dominant in basically every other country, up to the point that some countries don't have salt caverns. Okay, and that's also the reason why in Germany right now we are focusing on those caverns when it also comes to the first real-world projects like the Reallabors. Okay, but what does happen when we convert an existing natural gas storage facility to hydrogen? First of all, we need for the same energy that we want to store larger volume. And this is reasoned by the heating value that natural gas and hydrogen has. Natural gas has approximately 3.5 times the heating value than hydrogen. And also in terms of just volume, we can store less hydrogen volume in the same UGS facility under the same operating pressures than natural gas. Why is that? Let's briefly get into some mathematics here. This can be easily, or rather easily, calculated by taking a look at the natural gas equations and work on the or work out the working gas volumes for natural gas and hydrogen under the same pressure and temperature conditions, but for both gases with their individual Z factors. And by just comparing the volumetrics, we are ending up with a factor of 1.6, that the hydrogen storage volumes are lower than natural gas storage volumes just due to compressibility. And then when applying the heating values, we are getting again a reduced energetic storage capacity. That's why this 20% is given here. And this gives us an additional need for new UGS facilities. Okay, what I plotted here is an example from a research project by another company, DeepKBB, with whom we also worked together in the past, and they looked at the available salt formations in Europe. And what you can see here in all of those bluish and turquoise bubbles, those are the possible and available salt formations in Europe and where cavern storage is possible. And you see it here in particular in Germany, largely located in the North German basin. So, and according to their assessment, we have quite a large number of terawatt hours that is potentially available for storage if we would utilize all of those sites. So, but how much energy, how much hydrogen storage capacity do we need at all? This largely depends on the demand and how the future energy system will look like and who are the customers and the utilizers and so. And here we can take a look at the long-term scenarios by the Federal Ministry of Economics and Climate, who compiled and now 3 different scenarios until 2045, and it's somewhat in the range of 47 to 73 terawatt hours hydrogen storage capacity, not consumption capacity. And depending on which number turns out to be the actual one in reality, we definitely would need to either convert all of our facilities and or even establish new ones. Okay, but what does the hydrogen then make with our wellbore installations and the caverns? Let's take a look at the wellbore installations firsthand. The rather obvious item is that our pressure development in the well will change, since hydrogen is a much lighter medium than natural gas is. And of course, you always have a static column depending on the bottom hole pressure of the reservoir, the operating pressure, the gravity of your gas, and so on. And then you can calculate your wellhead pressures from that. The same can be said if you are in actual operations for injection or withdrawal. There you have the static column as well, but also your dynamic friction losses. To visualize this briefly, depending on if you're on the withdrawal side or in the injection side, your pressure behavior in the well changes. So far, so good. This is the same story for natural gas and hydrogen. But since hydrogen is a very lighter medium than natural gas, we can take a look at the right-hand side for comparison. And what we quite good see here, that for the same bottom hole pressure, I hope you can see my mouse, we are always ending up with, regardless where we are, with a higher wellhead pressure. And this has a profound impact on our above ground installations, in particular for during injection on the compressor discharge pressure. Yeah. Okay. And in case a compressor cannot deliver the new required maximum wellhead pressure, okay, then we can even store less volume. Speaking about compressor, but very briefly in terms of energy when it comes to hydrogen blending, I plotted here a chart for some very for sample calculation that we undertook in the past. You can always calculate the compressor power requirement by mass flow and so on, and also the cooling power. And what you quite see here when it comes to blending, you have a quite significant peak, close to 20 volume% of hydrogen blending for reasons of change in mass flow, but also in for the isentropic exponent. When we're getting to large shares of hydrogen up to 100%, the reduced mass flow is the dominant aspect at the same volumetric flow rate. However, here in between, partly the impact of the isentropic exponent is much more, and that's also the reason why then here the power requirement has this significant peak here, which seems a bit odd if you just look at it. Okay, here just some explanations about the variables. Okay, long story short, we are ending up with a different pressure and a different load in the wellbore, which means we need to take a closer look at the stress that our wellbore experiences, radial, tangential, and in the end develop an equivalent stress calculation. The Mises approach is very common here for subsurface, and we need to reevaluate our safety factors. If we have different loads in the well, we need to see if the previous safety for natural gas storage is still given. We are now here in the field of converting in existing facilities. Of course, when you build a new one, you would design from scratch. Okay, for such assessments, you can build numerical tools for very dynamic considerations, combining the wellbore, the cementation, and the surrounding rock. Yeah, inner stress, outer stress, and so on. Rather complex calculation over the length of the entire wellbore. I just put here a screenshot from an example model that we usually use and feed it with different input data. After the wellbore, and I know it's very brief, sorry for that, we need to take a look also at the caverns themselves and how the salt reacts to our storage operation. It is very likely that storage operation becomes much more multi-cyclic in the green hydrogen world compared to natural gas, because wind is not only wind is not always waving, sun is not always shining, and yeah, it's very fluctuant. And this means we need to utilize different injection and withdrawal patterns compared to natural gas, where we have this annual cycle withdraw in the winter, injection in the summer. And this is just an example scheme to demonstrate a little bit. Natural gas storage, I plotted here a red line illustrating briefly an annual cycling, and compared to that, some very fluctuating blue hydrogen line. I plotted here the storage pressure versus a time period. Yeah. And of course, this change in the average cavern pressure has a profound impact on cavern conversions and also on surface subsidence resulting from cavern conversions. We can go into more rock mechanical details if you have particular questions about it. Right now, I can only mention it. Sorry. Okay. But speaking of rock mechanics and cavern stability, we also need to make some additional assessments there, since our salt, the cavern, needs to provide long-term stability. We need to determine our minimum and maximum operating pressure. We need to determine how many caverns we could put in the salt dome, which distance do they need to have to each other, which distance do they need to have to the caprock, and so on, just to stay safe mechanically, and also stay technical tight and provide safety against uncontrolled gas migration from the cavern to anywhere where we don't want to have it. And this is usually done by lab testing from core samples and from, I put here some charts from a 1, 2, 3. I put here some charts from a finished research project called H2UGS, where we did such lab testing accompanied with numerical simulations from our partner institution of ours, investigating different loads on various critical points of the cavern. Yeah, salt in the cavern itself, at the very top of the cavern, and from a cement at the LCCS. Maybe detailed questions later on that. Those load cycles had been applied to the actual or to the anticipated, let's say it like this, to the anticipated operating cycles to represent them. And what you need to do then is to history match your model, your numerical model with the laboratory data, and then scale it up to a real cavern model, including also the surrounding rock. And then you can analyze your stress and also analyze other things like gas migration into the rock matrix, an example I just plotted here. Yeah, and then you can work on your operating pressures and loads and so on. Okay, I think I'm already over time, and this means give me please 2 more minutes. And I just want to mention that we need in the for the cavern hydrogen storage also consider processes or interactions that might go on between the stored hydrogen gas and the cavern sump, and some certain reactions triggered by microbial activity. This is a rather unusual case, and it's just a conglomerate of different possibilities, not an actual field study. But those processes can be triggered by the availability of a carbon source, which serve as a nutrient to hydrocarbons, and then some conversion processes can go on that we don't want to have. And here it's important to consider this when converting in previous natural gas cavern, or also an oil cavern, and so on. Or if you use the diesel blanket during the leaching process during construction. Okay. This again has an impact on the necessity for gas treatment. There are different quality grades in current discussion in Germany: grade A, grade D. Grade A, I can tell you, is rather easy for common methods for treatment to achieve, but grade D, when we're looking into purities of more or equal to 99.97%, it's really getting a bit more tricky. Okay. So, is this what I'm talked about exclusive to caverns? Yes. What about porous UGS facilities then? Just a quick discretion. We have everything, but all problems we have, not problems, considerations that we need to undertake in caverns, and also the flow processes in porous media. So overall, porous UGS facilities are much more complex to analyze. It is necessary to do that, but with salt caverns, they are the more easier storage types, more flexible storage types. And to wrap up, here's just a picture of the ongoing activities in Germany, lots of real labs, Bad Lauchstädt with the one of the cover photo, and some others here in North Germany, obviously, but there are also others in the Netherlands, in France, and other countries as well. And maybe I just give you 15 seconds to take a look at those bullet points here to wrap it up. My point of view is there was a lot of fundamental research going on in the last years. And we are currently at the point in time where it's simply necessary to get into the field, make new experiences there, and push the topic forward. Okay. And with this slide, I mentioned it in the previous ones: gas treatment and compressor. Those are the links to the above ground installations. And without further sayings, this shall be the transition slide. Thank you very much for your attention from my side here. And yeah, Q&A was announced after all the presentations.
Okay, thank you very, very much for this very interesting presentation about the below ground aspects of the hydrogen storage in salt caverns. Thank you very much, Hagen Bültemeyer, for this very deep insight into the activities. And now it's my great pleasure to move over to Lorenzo Laporta from ILF in Munich. And he will continue with this topic and will give us an update about the above ground aspects. So, Monsieur Laporta, the floor is yours, and we are very much interested in your presentation. So please share the screen and go ahead. Thank you.
Thank you, Martin, and thank you, Hagen. I think you can now see my screen. So we saw an interesting presentation about below ground hydrogen storage. Let's analyze now what happens above ground. My name is Lorenzo Laporta, ILF, and I'm a process engineer working in the green hydrogen space. This is what we are gonna talk about. So a brief introduction about ILF Consulting Engineers Company. Then we will start from the above ground facilities, an introduction, why we need them, why we're talking about them, and then we will start to have a look at the facilities used for actual natural gas storages, to better understand what it takes then to go to the hydrogen storage facilities, to understand better the differences and what can be done to reconvert a natural gas storage into an hydrogen gas storage. Then we will see some typical questions and answers for underground natural gas storage reconversion to hydrogen, which I've been, many times I heard this kind of questions, and I think it's good to address this kind of points. We will then see an ILF project experience example, and then wrap up some conclusions. Well, Then ILF is an international engineering company and consulting company, active in more than 150 countries with more than 45 offices around the globe, 9,500 projects successfully executed over more than 55 years. And we operate in 4 main business areas with more than 2,500 employees and 250 million euro of revenues. We are active in the along the whole hydrogen value chain. Why hydrogen value chain? Because hydrogen generation, green hydrogen generation, starts from renewable energy production. Then it's important the transmission of energy. It's important the desalination to provide desalinated water to the electrolyzer. Then the hydrogen production itself that can be later converted in some green derivatives. It can be stored, it can be exported. Here I mentioned some projects that ILF has been working on. We have been working on projects relative to the whole hydrogen value chain. Well, why do we talk about hydrogen value chain? So hydrogen is an energy carrier that can be used to store renewable energy in its chemical structure. It can be reconverted into electric energy if needed. It can be transported in different forms, also over long distances. And as Hagen said before, because of the fluctuating nature of the renewable energy production and therefore also the hydrogen production, a daily and seasonal hydrogen storage is necessary. So that's why we are talking about hydrogen storage, and in particular about the above ground facilities of an underground hydrogen storage. So let's have a look first at the facilities needed for an underground natural gas storage to better understand the technology, the standard technology, and we will look then at the differences for those required for a hydrogen storage and understand what it takes to reconvert an underground gas storage to an underground hydrogen storage. So before being stored, the natural gas flow is measured in a metering station, is then compressed with a compression unit. The compression leads to a temperature increase because of the physical properties of natural gas. So natural gas needs to be cooled before being injected underground. Here we see a cooling unit. There are different types of compressors. The compressors could be axial turbo compressors or reciprocating. Axial has generally higher volume flow capacities, but many old storage have reciprocating compressors. So when natural gas is needed, is then extracted from the underground gas storage. Once extracted, the natural gas is preheated with this unit here and depressurized. The preheating is done to avoid too low temperatures because of the Joule-Thomson effect. The depressurization reduces the natural gas temperature by, as a rule of thumb, by 30 degrees every 100 bar of pressure reduction. For this reason, glycols called TEG can also be added before the natural gas injection in the storage to avoid hydrates formation. After the depressurization, natural gas is dried in a drying unit. This is because both salt caverns and the depleted oil and gas field can contain also water. The dehydration usually is done with glycol technology, usually TEG, that is also used to prevent hydrate formation. And once the dehydration is done, natural gas can be measured, the flow can be measured in a metering station and drain injected in the gas network. Very well. So let's go now to the underground hydrogen storage facilities and let's see the differences. The main differences between hydrogen and natural gas storage above ground facilities are related to relative to the compressor type, the fact that there is no preheating needed before the depressurization, because the Joule-Thomson effect for hydrogen is different. In fact, a pressure reduction leads to a slight heating of the gas and not a cooling like natural gas. And then another difference will be related to the different dehydration technology that can be utilized. The type of facilities mainly depend on the type of underground gas storage and on the specification regarding hydrogen quality. So again, described before the different kind of underground storage. We saw salt caverns, but we also saw depleted oil and gas field. And I added this lined rock cavern that's it's like an artificial cavern that could be used in specific cases. Whereas the hydrogen quality specification depends on the end user. For example, the gas network has a dew point specification of -7 degrees 70 bar G, and this could be applied also to hydrogen. Whereas if the end user is a fuel cell, if it would be a fuel cell plant, we would have a different hydrogen purity requirement, typically higher than 99.9% mole purity on a molar basis. Let's talk now about the compressor type. There are three possible types. The reciprocating oil-free compressor, reciprocating oil lubricated, and diaphragm compressor. Axial compressor cannot be applied to hydrogen compression, at least not yet. There are no available commercial axial turbo compressor for hydrogen, but they will be available soon on the market. A reciprocating oil-free compressor can process up to 500, 600 kilograms hour of hydrogen and compress up to 300 bar final pressure. The advantage is that it can avoid oil traces in hydrogen. So if there is a purity requirement, that's the preferred option. Whereas oil lubricated compressor can achieve higher flow rates and pressures, higher pressures, but worsening the hydrogen quality. The choice will depend on the storage type, because in case of salt cavern, the oil-free compressor will be the preferred option. But in case of a depleted oil gas field, also the oil lubricated would be a feasible option. Let's talk now about cleaning methods in case of oil residues in hydrogen. The cleaning could be done with if traces of oil are present in hydrogen, the cleaning could be done with adsorption, with silica or active carbon. And in case of higher concentration, a dew pointing could be adopted. And the third difference is, I mentioned before, was dehydration methods. Cooling is the most simple and low capex intensive option. It could be done with different cooling medium, air, water, or other refrigerants. It's a cooling at high pressure and low capex. Such typical water cooling could achieve a hydrogen dew point between 0 and 5 degrees C depending on the pressure, but usually at low pressures. If more strict specification are given, adsorption is the preferred option. Usually TSA is used, temperature swing adsorption, which on the other end has a high regeneration duty. The adsorbent, silica gel usually are more expensive than glycol, but it can achieve, and it has better performances. It can achieve dew point below -20 degrees. Whereas adsorption, which is the standard technology used for natural gas, is being tested for hydrogen, but is not commercial yet, is not completely tested yet. And we will see why later. This is a typical example of hydrogen storage facilities. We have been as ALF, we have been working on this kind of projects, and so let's see what we have here. After the electrolysis plant, hydrogen goes into a buffer, which main purpose is the startup. So to match the startup of the electrolysis plant and the compressor. We have then the compressor unit intercooled, which is typically a reciprocating compressor. Then hydrogen is stored in this case, a salt cavern. And when extracted, it can be cooled down at high pressure, and water can be separated with a separator. If lower dew points is needed, temperature swing adsorption unit can be added before delivering hydrogen to the end user. Here you can see this figure regarding the Joule-Thomson effect. So there is a slight temperature increase of 2 degrees C, more or less, for 100 bar pressure reduction. And that's why we don't have this freezing problem like with natural gas. Very good. So I tried to wrap up these questions, which I received many times, and these questions are regarding reconversion of underground gas storage facilities to hydrogen. Let's see the first. So, can a natural gas axial compressor be utilized for hydrogen? The answer is no. An existing axial turbo compressor cannot be used for hydrogen because of the different physical properties. As I said before, a new generation of axial compressor is being developed and will be available soon. Whereas if our underground gas storage is using a reciprocating compressor, could this compressor reused for hydrogen? This option could be possible. Of course, the compressor will not operate at the optimal design condition, but definitely the option could be considered. Let's now have a look at this question regarding dehydration. So if our existing drying facilities for natural gas, if we would like to reconvert these our existing dehydration facilities for natural gas for hydrogen, would be this possible? As I said before, the possible application of glycol technology, TEG, for hydrogen is being studied. The problem they are facing, is mainly a high degree of hydrogen loss during TEG regeneration, because the glycol absorb more hydrogen than with the case of natural gas, and the regeneration then leads to a high degree of hydrogen venting and loss. So that at the moment is not economical, but they may find a solution in the future. They are also looking at other kind of liquid adsorbents. The last question is about the piping used in the natural gas storage. Could these pipes be reutilized for hydrogen? In general, there are 3 criteria that must be respected for a possible reconversion. The pipes would need to be used at constant loads. They would need to be made of soft metal with a tensile strength lower than 350 megapascal. And plus, the utilization factor would need to be less than 0.5. If these criteria are not respected, then a further investigation should be performed. And in case the investigation give a negative result, then the pipes would need to be replaced. This is an example ILF has been working on. This is we've been doing the conceptual design and the basic engineering for an underground hydrogen gas storage, a small one. We see here the capacity of 17,000 cubic meter, quite smaller than the capacities Hagen mentioned before. But the purpose of this storage was to store hydrogen for a 30 megawatts electrolysis plant. With this maximum cavern pressure, 175 bar, the compressor unit can process up to 6,000 normal cubic meter hour, two stages intercooled, with 0.7 peak megawatt peak compression power, and the hydration unit could reach this dew point specification, so 5 degrees C at 31 bar G. So conclusion. The challenge related to above ground hydrogen facilities need to address so that the type of above ground facilities depend on the kind of underground storage. So that's the first thing to be considered, and that's the main parameter, the main point that will determine the kind of facilities. Then another challenge is the reconversion of previous natural gas storage into hydrogen storage. And the reconversion may require to substitute at least the compressor and the drying units. And then the technology to process high amount of hydrogen in the same order of magnitude as natural gas is still under development. And now I'm talking about the compressor unit and the dehydration unit. So thank you for your attention. And if you have further questions, please, you can contact me at this email address.
Okay, Lorenzo Laporta, thank you very, very much for this very interesting presentation. Now we do understand that, let's say, this is quite a challenge to, let's say, convert natural gas storage facilities also from the above ground facilities into a hydrogen storage facility. But nevertheless, the work is on the road. And so we will see in the years to come that also this technology or this challenge will be, let's say, solutions will be available for that. With this, let's come back afterwards when we have a very short roundtable discussion with all of us. And now I have the honor and the pleasure to introduce Julian Jepsen. He is from the Helmut Schmidt University here in Hamburg, and in parallel, he is also with Herion, which is a research institute also here close to Hamburg. And he will give us an update about hydrogen storage in metal hydrates. So, Julian, the floor is yours, and we are very much interested in your presentation. Just go ahead. Thank you.
Thank you very much. Yeah, it's my pleasure to introduce to you another technique of storing hydrogen. This is done by so-called metal hydrides. And in a couple of minutes, I will try to give you some insights how this works, what are the challenges, and what are the advantages. So I skip the introduction because obviously hydrogen technology is of key interest for all of us is obvious. I just want to point it out that the hydrogen technology is complex but doable, as it also was seen in the presentation before. Some challenges remain, particular for the hydrogen storage, and here hydrogen storage by metal hydrides can be a solution, at least for some applications. What makes it so interesting is that storing hydrogen is challenging in different, as we saw in the presentation before, at different scales. So in large scale, it's challenging but doable. thanks to the previous presenters, but also in small scale, it's challenging if you think about mobile applications. And the reason mainly is, first of all, given by the energy density, which you can see here. So our natural gas and gasoline energy carriers are very, very high concerning their volumetric energy density. And this cannot be reached by lithium-ion batteries, for instance, but this also cannot be reached by hydrogen, even though hydrogen on a gravimetric point of view has the highest energy density. This is all for standard temperature and pressure conditions, and the idea or the challenge of storing hydrogen is now to increase the volumetric energy density without losing too much of the gravimetric advantage. And hydrogen storage in general can be done at different approaches. And here you see a nice overview. You can compress the hydrogen, which you see on the 3 slides, 3 pictures on the left, where you have to increase the pressure from ambient pressure to 350, even 700 bars to get to a certain distance of the hydrogen molecules. The reason behind this, the reason behind the fact that you need so high pressure is that among the molecules you have intermolecular repulsive forces, and this avoids the hydrogen to get into, let's say, high density so that it can be used, for instance, in a car. 700 bar is what is at the moment state of the art and what is used in car applications. However, to resist the pressure of 700 bar, you need a rather complex hydrogen storage system. An alternative is shown on the 4th pictures. I can also use the laser pointer to highlight this, which you see here. And this is the storage by hydrogen in the liquid state. Also there you have these forces, however, they are even more reduced, so you can get the hydrogen in an even compacter way. But you have to go down to really low temperatures. So 20 K is a very low temperature that is a huge effort in the sense of energy that you have to invest to get down to the temperature, and actually to stay at this temperature is also challenging. So also for these kind of storage, it exists, it's on the market, it's state of the art, but the storage vessel itself is rather complex. An alternative is to store the hydrogen not in the molecular state, but in the atomic state. And this is what we do in the metal hydrogen storage, where we store hydrogen atom by hydrogen atom inside a metal lattice. And without the molecule state, we are not facing the intermolecular repulsive forces. And so we can actually put the hydrogen in a much closer density next to each other. Very important is here to distinguish between absorption and adsorption, which is shown here nicely. So you hear before that adsorption is a typical process where you physisorb something on the surface, but we're talking now about absorption. So the hydrogen is really diffusing into the metal lattice. How does this work? Very briefly, so you have an interaction of the hydrogen and the metal, or let's say the host material. And first we have some adsorption taking place on the surface, but once the hydrogen is split into the 2 atoms, hydrogen is diffusing into the metal and find its place inside the lattice and inside the host material. This is done on a so-called thermodynamic equilibrium, so it doesn't need further pressure. So you have to initially increase the pressure, but once you reach thermodynamic equilibrium, just with a slight overpressure, you get to the full capacity of the material that can be stored. This sounds a little bit theoretic, but let's have a look to the elements, and we come back to the thermodynamic in a second. So basically, almost all elements can be used to form a stable hydride. You see only some elements here shown in yellow in the middle are not able to form a stable hydride. And it gets even more complex because now you can add also or combine different elements. So the number of elements that you can choose for storage of hydrogen in this state is enormous. From the gravimetric and volumetric point of view, we see clearly an advantage against the before mentioned gravimetric storage, which is shown here in the lower part at different pressures, or the liquid storage, which is shown here in the line. We see that all the commonly used metal hydrides or combination composites are way above the two storage techniques concerning the volumetric and volumetric hydrogen density, but also to some extent against the gravimetric density. Obviously, we are not competitive to the carbon hydrides. They are still above, but however, as you all know, or as we all are aware, we want to get rid of them. So a little bit about the thermodynamics. How does it work? Basically, this is shown by this nice equation, which combines the reaction enthalpy, delta H, with the reaction entropy. Delta G is the combination of both the free enthalpy, and whenever delta G gets negative, the reaction occurs spontaneously. So how is this possible? So during an absorption, we have a negative entropy because we are changing from let's say, chaotic orientation in the gas phase to a well-ordered orientation in the solid phase. And this is usually what comes along with a negative entropy. So this term gets negative, and with this minus here has a positive contribution. However, due to a negative delta H value, because the absorption is an exothermic process, we end up in total at the negative delta G value. Usually the contribution of the enthalpy is much higher than the contribution of the entropy. But if this is the case, and for the desorption, so the release of hydrogen, everything is obvious, the other way around, how does it work? Because during the desorption, now we have a positive contribution. The hydrogen goes to its more favored stages, the gas phase, and we have a positive contribution from the entropy. So with this negative sign here, we get a negative contribution to delta G. However, as I mentioned, if the absorption is exothermic, the desorption is an endothermic process. So we have to provide heat actually for this reaction. And since still this contribution of the enthalpy is higher than of the entropy, we end up with a positive value for delta G. So what makes this reaction now reversible? For those of you who are a little bit into thermodynamics, you probably already know the temperature that makes the difference. So by increasing the temperature, we are changing the value for delta G, and we are switching from a positive value to a negative value. And in the consequence, also the desorption is possible. In real life, it's a little bit more complicated than this, because in real life, also the pressure the pressure plays a role. So what we see here is the equilibrium line. So if you follow this line, or if you are on this line, nothing happens, neither absorption or desorption. Delta G is 0. But as soon as you are above, you are absorbing, and as soon as you're below, you're desorbing. And what we just saw is basically without any effect of the pressure. So if you draw a straight line here, you see just increasing the temperature, which is on the x-axis, leads to desorption, while at lower temperatures you are in absorption region. And as I mentioned, in real life, it's a bit more complicated, because now also the pressure measures, but actually it's as simple as with the temperature. Here in this, it is like, it's only reducing the pressure, or being at low pressure, you're desorbing, and being at high pressure, relatively high pressure, as you see, you're absorbing. So now playing with temperature and pressure, you decide whether you absorb or desorb your material. However, this takes place depending on the material you choose at much moderated pressure conditions and also temperature condition. This is here shown for an example for high temperature hydrides. There are also hydrides that absorb and desorb in the region of below 100 degrees C. So why is this so important now? Why is it interesting? thermodynamics is actually something we can trigger, something we can tailor. Usually a high enthalpy of formation stands for high stability and thus a high temperature of operation. So if we want to destabilize this, we have to destabilize the alloying. And this can be done by elements that can form a stable compound with the metal, but not with the hydrogen. So for instance, in this little example here, we have magnesium. Magnesium is a well-known and very good hydrogen storage material. But if you alloy some nickel or some nickel and copper, you reduce the enthalpy, as you can see here. And this reduction in enthalpy then leads to a further reduction of the thermodynamic stability. And this is then also affecting the equilibrium pressure. And so you can absorb or desorb the hydrogen at much milder condition. However, you also see here that this comes along with a reduction in capacity. So the amount of hydrogen that you can store, which is shown here on the x-axis, is also reduced by this effect. However, this is just an example to show that tailoring the thermodynamics is possible, and with this you can exactly define a material that fits perfectly to your application, both in mobile but also stationary application. But this is just thermodynamics. One more example, and then I'm done with thermodynamics. You can also combine two different metal hydrides, like here is shown for the example of magnesium hydride and lithium boron hydride. They are both well-known hydrides with relatively high capacities. So 7.6 weight% means that if you have 100 kilo of material, 7.6 kilogram of hydrogen can be stored inside. And here it is even more than that. However, they both have a rather high enthalpy and those are also stable compound. It is a stable compound, leading to relatively high temperatures of operation. If you combine these two if you combine these two hydrides, during the reaction, a further reaction occurs and a new compound is forming. This new compound now can take part of the energy that is necessary to get from the hydride phase to the dehydrated phase. And to give you real numbers for this, if you combine these two materials, you end up with a reduced enthalpy, so a reduced stability, and also a much lower temperature of operation, and still remaining a relatively high hydrogen capacity on the gravimetric point of view. This is thermodynamics, and now if you want to look to a real tank system, we also have to consider reaction kinetics, because thermodynamics just tells you whether a reaction takes place and what are the temperature and pressure conditions that you have to apply. But how fast the reaction occurs is only shown by reaction kinetics. And this is how reaction kinetics is behaving. We have different steps, as we also saw in one of the previous slides. So the hydrogen has to split, it has to diffuse into the bulk, and inside the bulk of the material, it has to nucleation and growth. But all these processes can be modified, also like we saw before for the thermodynamics, where we have the possibility to change this. Also, the reaction kinetic can be changed, for instance, by catalyst. So by catalyst, you can quite easily improve the process of the splitting of the hydrogen molecule into the two atoms. Another possibility to increase the diffusion of the hydrogen is if you increase the numbers of boundaries. So you see here in blue the boundaries between the different phases, or let's say phases. And the more boundaries you apply inside the material, the faster the reaction. But how do you get more boundaries inside the material? That's also rather simple. You apply some milling techniques where you destroy basically the fine structure of well-organized metal grid, and you end up with such a structure where you have a lot of these boundaries, and along the boundaries the hydrogen can diffuse as if there were highways. further process or further effect of this milling is that if you add a catalyst and you perform milling, and this is a SEM measurement of the material before it was milled, and you see some particles of the material, you see some traces of titanium, which is here used as a catalyst, and after milling, you have a very nice distribution. And probably some of you remember from school or university times that a reaction of a catalyst matters also how nicely the catalyst is distributed. So there's a further effect of the milling where you distribute nicely the catalyst. Milling also has additional effect on the particle size because it reduces drastically the particle size and leads to more surface area, and also more surface area is speeding up the reaction. So this is now my conclusion. So the reaction kinetics can be also very easily manipulated. If you take the bulk material, it's very hard to get the hydrogen in, but also really hard to get the hydrogen out. However, if you create a nanocrystalline structure with a lot of boundaries, then you can already start to absorb a huge amount of hydrogen. However, it's not so easy to get the hydrogen out of the material, but by a catalyst, this can be also nicely performed. So not only thermodynamics, but also kinetic can be manipulated according to the application needs. If you then want to build a tank out of it, and these are my conclusion and last slides, there are some processes that you have to take into account, because not only the intrinsic kinetic, the chemical reaction matters now, you also have to make sure that you have a nice distribution of hydrogen and also a nice distribution of heat. Depending on absorption or desorption process, you have to make sure that the heat is nicely released or that the heat is going into the system. And this is an important design aspect, because the larger the system gets, and this you see here from the left to the right, this diameter is increasing, the less of the intrinsic kinetic, which is shown here in gray, matters, which is shown here as a total resistant, and the more the heat transfer matters. Hydrogen transport never is an issue. However, heat transfer, in particular if you get to larger system, is the main aspects that you have to consider if you design such a tank system. And finally, this is really the last slide, there is also an advantage from the economic point of view, because these storage systems come along with, as it was mentioned before, much moderate temperatures and much lower pressure condition. And in the consequence, you need very simple tank hull structures without any composite, without any high isolation. So you end up with a clear advantage. And this is calculated here, where you see in blue the price for the hydrogen cost, which is obviously equal for all the here considered storage systems, 700 bar liquid, and 2 examples for metal hydride storage. But you see in particular, if you look to the orange, so the tank system cost, that there's a clear advantage by this technology due to the simple structure. And this is even more, or the advantage is even greater if you assume mass production aspects, because these systems are not produced under mass production, whether pressurized storage and liquid storage are already almost produced in the mass production aspects. So there is further price reduction, or there can be a further price reduction expected. So with this, I finish my presentation, and I guess now the 3 of us I really warmly welcome your question. Thank you.
Yeah, Julian, thank you very, very much for this very nice presentation. Now I really get a clue how the metal hydrides work, yeah, and I'm get an update about thermodynamics, which was the most beloved part of my studies, honestly. Okay, I'm just kidding. Yeah, gentlemen, thank you very much for this 3 very interesting presentations. And we are already quite advanced in time, so I would like to make it short tonight with the presentation or with the discussion. And maybe we can make 2 or 3 rounds. And the first round is that, let's say, when we talk about let's say, the possibilities and the role of storage when we talk about metal hydrates and talk about salt caverns? How do you see the role in the next 10 years of these storage possibilities within the energy system? And where do you see the certain spots or the area or the most important application areas within this, with this storage inside the overall energy system? Maybe we can start first with, let's say, Mr. Bültemeyer or Mr. Laporta. It's up to you to decide how you see it from the, let's say, salt cavern part, and then maybe you, Julian Jepsen, can give a update about what you see, where you see the role, and where you see the possibilities and the markets for the metal hydrate systems.
Okay, thank you very much for kicking off this Q&A session, and I'd like to answer it from my perspective. And the geological sites, geological storage sites, I really see in the market of regional energy supply. For very main large customers can be individual plants if they are really large ones, but also for regional supply. What the future brings in terms of different application possibilities where hydrogen is used in a caloric way, let's say via burning or just as a gas itself and fuel cells or whatever, I can't answer it right now. This is not really my field of work, but when we are really getting into long-term storage, regional supply, here I see the geological facilities. The development, according to my perspective, is we are kicking it off with the salt caverns, and just a couple, just short-term behind, couple of months, maybe a couple of years behind, also porous UGS facilities kick in simply due to necessity and due to the fact that many countries simply don't have salt caverns.
Okay, thank you very much. Lorenzi Laporta, you would like to add something to this?
Yes, of course. I agree with Dagen, and I would add that I would consider also the fact that the underground hydrogen storage, it's a solution possible only when the geological conformation allows it. So for Germany, it's definitely a possible way, a possible solution. There are many other countries where this is not going to be feasible, and they will need to consider other kind of storage solution. That may be storage of hydrogen in liquid form, either liquid hydrogen, or maybe also the storage of other kind of liquids, green derivatives like green ammonia or methanol or LOHC. I think that this kind of solutions will be the main options for long-term hydrogen storage for hydrogen energy production. Whereas, of course, Julian will know more about it, but I don't know the capacity of the hydrogen storage up to which level it can go. If it's only applicable to mobility or even for heavier applications. So maybe Julian, I leave you the space to answer about
First of all, thank you very much. And I do understand that, let's say, you say one of the hurdles or one of the limitation, and this is also what I would like to add up to Julian, is that, let's say, you need to have the, let's say, underground conditions. And I also understood from your presentation that at least in the northern part of Germany, further up to the Netherlands and maybe other part of Poland, there is good underground conditions to, let's say, establish such storage systems. And if I remember right, we also learned in one of the previous webinars that also in North Africa, there is indeed underground conditions that you might be able to establish such salt caverns. So from that point of view, from a resource side, okay, there are limitations, but the limitations are not so strict that, let's say, this is a no-go option. And this is the point which I would also like to ask you, Julian, about the resource side. I mean, when you have this, you need a lot of metal or, let's say, material or resources. Is there any limitation from the storage? And where do you see the, let's say, the markets for these metal hydrate storage systems?
Thank you. Yeah, so actually metal hydrides can be used for both stationary but also mobile application. If we talk about stationary application, obviously we're not talking about the scale like the two presentations before. So this is cannot be provided, and it doesn't make sense to do it with metal hydrides. In the mobile application, it can be everything on the road, on the railroad, or on the water. But if it gets to a certain size, or if it gets to an application where weight matters a lot, like in airplanes, also there metal hydrides are not the best option. For stationary application, if you think about sector coupling in delocalized energy storages, they can play a role, and we follow this also in some projects as aspects. But as I said, the dimension is always limited. So it is a local storage to convert some energy from the electric grid to hydrogen and then use it for the mobility sector, for gas station, or to convert it or to implement it into the gas grid. So this is a job, a short-term storage that metal hydrides can do very well. And then there's also other applications. And then coming to your second question, the limitation of the resources is obviously an issue. So in our research, in the past, we only can take a look to technology aspects like temperature, pressure conditions, and things like that. But this is not how we are able to work in current days. So in current days, we always have to look to what kind of materials we are using in the sense of abundancy, in the sense of whether it's a critical raw material and things like that. And also pricing matters a lot. So all these aspects we have to take into account. But the good thing is that the number of metal hydrides you can use is enormous. And so we can take the elements that are fulfilling all, or if not all, most of the requirements, and then design a very suitable metal hydride storage system for the individual application.
Okay, thank you very much for that. So now let's come to the final round due to time limitations. And maybe you can make a, let's say, a vision where you see, let's say, the storage facilities on the salt caverns and the storage facilities, or the role of the storage of metal hydrates and salt caverns in the next 10 years. Do you would expect that this is already market mature, that we have already converted our existing salt caverns from natural gas to hydrogen, or we, let's say, operate our, let's say, heavy trucks with metal hydrate storage facilities? How you see the role of your, let's say, of the storage facility, what you presented in the next 10 years? Maybe we start again with Monsieur Bültemeyer, then we go to Monsieur Laporta, and then to Monsieur Jepsen. Thank you.
Okay, then I may try. Okay, definitely when we're talking about underground storage facilities, we are bound to a certain geology. If it's not there, we cannot do anything. So a site assessment, conditions assessment of the actual conditions in that area of that salt dome, or maybe of that porous facility, is very vital. Those upfront consideration and investigations need to kick off basically now, in case where they did that, because also the conversion process of a natural gas UGS facility to hydrogen takes quite a while. We're looking at definitely something like 3 years if it's a smaller one, but it can last up to 7 years, and well by well, and so on. And you always have to consider that also during this conversion, this facility is not available for operation. And also when looking at the current storage capacity of the real labs, we are looking at currently installed or prospectively installed at the end of those projects 0.5 terawatt hours of hydrogen storage capacity. Compared with the demand by the so-called German National Council on Hydrogen, this is a tenth of the requirements. They postulate a 5 terawatt hours in 2030, which means we need basically decision making right now. So it's quite a challenge. But I think as soon as the groundwork is done and the commercial base, a commercial case is there, then it can go quite fast. Yeah, but commercial case for the operator and for the entire system is the vital necessity for everything.
Okay, thank you very much for that. Monsieur Laporta.
I would like to talk about a more economical and political aspects, scenario aspect, not the technical one at the moment, to reply to this question. If we think about liquid natural gas, we saw in the past, we thought that increasing the liquid natural gas capacity would have taken a long time. And with the current energy crisis, we saw that new liquid natural gas terminals were constructed in a very short time. So just because of the political pressure, the hydrogen projects, hydrogen facilities, I think that can be designed and constructed in a very fast way, much faster than what we could expect at the moment. And working in this field, I have the feeling that the hydrogen business is growing every year in an exponential way. And so to reply to the question, what I expect in 10 years, I would say that in 10 years, the world of hydrogen could be much, much bigger than what we could say at the moment. And so to give a forecast is hard, but I would expect a great thing to happen in 10 years. So, yeah.
Okay, thank you. Thank you very much for that, Julian.
I can make it short because I just had a look at my glass sphere here and I know exactly that metal hydrides will play a major role. We see that metal hydrides are already in submarines in use. So I'm very optimistic in 10 years we will see them also many other applications. I cannot tell you all the secrets where, but in many applications I see high potential for metal hydrides. Thank you.
Okay, thank you very much for this, and thanks again to all of the three presenters. I mean, I would say it a little bit more Solomonic. I mean, at the end of the day, if we would like to transform our energy system towards more sustainability, towards more greenhouse gas neutral energy system, I guess we would need all the storage facilities and all the different storage options. They address a certain market or market share or market segment inside the energy system. So it's not a question if we use this or that. It's the challenge to use all of them and find for each option the very best spot and the very best place inside the energy system. So I hope that this is that you three can agree to this. And with that, I would like to terminate our session for tonight. First of all, thanks again very, very much to you, Hagen Wildemeyer from DBI in, let's say, Freiberg and Leipzig in Germany, to you, Mr. Lorenzo Laporta from ELF in Munich in Germany, and from you, Julian Jepsen from Herion and University of Armed Forces, Helmut Schmidt University here in Hamburg, also in Germany. Thank you very much for that. And I also would like to thank especially Wolfram Tuschewitsky and Felix Mendler for getting everything organized. I would like to thank also the translator for doing a very hard job to try to translate these lots of very strange words into French language. Last but not least, I also would like to thank the organizer, especially Shokri Aslush and GIZ in Tunisia for, let's say, sponsoring this event, for the sponsoring the translation, and of course the institutions here, which is the Hamburg University of Technology as well as the VDI here in Hamburg, for making this possible. With this, I wish everybody a beautiful evening. Enjoy yourself, and I would very much appreciate if I can welcome you next week, same place, same time, when we will continue our let's say tour through the production till the use of hydrogen. And still we have the thematic of hydrogen storage on the table, and then we will further go down the road to hydrogen transport and then to hydrogen use. With this, thanks again to everybody, and I wish you a beautiful evening. Enjoy yourself, and hopefully see you again